wherever we have lost it.
Okay. But for this question, so I just want to know, it wasn't that you had to combine the two and then work out the way the velocity goes, right?
Yeah, so in essence, what they needed us to do is, well, first of all, you needed to recognize that that the velocity is equal to that combination of electric field and magnetic field, that the electric field and magnetic field are perpendicular to each other, and the way that the forces would act on the velocity of a particle. So if they are equal, then, well, the way that you set them up can then help you select for a specific velocity of the particle, right?
Okay. I think I misinterpreted this question. Can I quickly send my picture on the physics group? Oh, that's not something I want to be doing.
Let's quickly see.
Because I thought when they say for the selection, I thought there was like, if you want to have a magnetic field or if you rather want to use an electric field, what the difference would be.
Oh, no. That's not what they want. They want to know that in this specific question, where you have a magnetic and an electric field, how would you select that? So you have both of those fields present at once.
Okay.
So that's what they have. I see for a magnetic field. Okay, so you did it separately. No, you're not going to score the mark. You're not.
Yeah, I
The idea was correct in the sense of that you said, by changing the one relative to the, well, in essence, if you change the one relative to the other, then you're going to select for the velocity of it. So let me just write from the memo side down what they are looking for, or what you needed to do. So they are requiring you to say that your electric field, okay, and so Ruben is there, no worries, he's going to get this recording thing now. And I will post the memo in any case. So the electric field and magnetic field is perpendicular to each other. That's important to say. And a velocity of and the velocity is also perpendicular to the two fields. Let me do that in a different color. So the velocity is perpendicular to the two fields. Then the forces on the field are in opposite directions. And because of this, shall we say, just the forces due to the fields this is now what actually is illustrated over there. The forces being in opposite directions. So if the forces are equal, If the forces are equal, you can select for a particular speed. So I drew the force diagram for it, which makes more sense. And I think it's going to be easier than drawing an electric field relative to a magnetic field. You can do that. You can obviously do that. There's no problem with that. And I think this bottom picture could be, again, a very similar type of experience where you just say a region of uniform magnetic and electric field, and then draw your current that is perpendicular to it. And if it is equal to each other, you will experience that.
Yeah.
A straight motion of the particles, let's say that. Right. Okay. So a nice 4 marks. Okay, let's see what they have on the next part for us. They say a beam of charged particles enter a region of uniform magnetic and electric field as illustrated. Okay, so that gray block is a uniform magnetic and electric field. And say the magnetic field is into the plane of paper, right? And we have the path of the particles. The direction of the magnetic field, the velocity of charged particles, and normal to the magnetic field is the particles enter the field. A particle in the beam has a mass of m and a charge of plus q velocity v. The particle passes undeviated through the region of the two fields. Oh, fantastic. On this figure, sketch the path of a particle that has a mass of m and a charge of 2q and a velocity of v. Label this path as q, and then a mass of that and a velocity slightly larger than that. Right, so how would that look like? What is happening?
Oof. Well, I'm pretty sure I got the I right. I'm not sure about I though.
All right, so getting
for that path that's V, I thought it starts curving downwards. And that was due to, there's like a drawing I saw in the book where it pretty much shows all. If you increase the V, then the magnetic force would be larger than the magnetic one would be larger than the electric force. So that it would sort of go in the direction of the magnetic force downwards, whatever.
Right, so let's deal with the first one first. Let's deal with the first one, I first. So what happens if the charge increases?
I wasn't sure, but shouldn't it not have a change?
It shouldn't have any change. Look at my equation, my velocity. My two fields are constant. So, and it's got the same velocity, according to that, as the particle that goes through undeviated with a velocity of v. So my first one is just going to go straight through. So it's independent of mass or the charge of it.
Yeah.
It's going to depend on the velocity thereof. And now the question is why and how? Why and how? And I think you started answering that. The memo says the deviations should be slightly upwards. So for my next one, there would be a very slight deviation up, and that one would be known as a V. Label it this path V. So for 2 marks, you would have gotten that slight deviation up. What did you? up and you
At a
said down.
deviation down, a slight deviation down.
All right, let's see if we can imagine for a moment in time what is happening in there. The magnetic field is into the plane, the FBI. So if we have, or if we look at our, my words are getting mixed up. My force of my magnetic field, it is BQV, right? So my force and my velocity is directly proportional. Just quickly use your left-hand rule, and my hand is too big to come into this camera. So
Yeah.
FBI. So I is my velocity, it's the direction, I. B is my magnetic field into the plane, and my magnetic force that it's going to experience is going to be up, right?
Oh, okay.
And because my velocity is slightly larger, my force due to my magnetic field is going to be slightly larger, and therefore my deviation is upwards.
Okay, I had the fingers around. I switched my thumb and my middle finger for...
FBI, indeed. Right. Okay. Let's move on to our last bit on this question, but I think our time might be running out on this. Let's start.
Oh yeah, we have less than a minute.
Less than a minute. Let's quickly start a next meeting. Do you have 10 more minutes?
Yes, and I really want to do that C part.
Yeah, okay. So let's quickly do that. And right, I'm going to stop and restart.